Lesson 16 is angles, arcs, and chords, and in 16.1 we're going to introduce 3 new theorems that are up at the top. So the first one, if 2 central angles in a circle are congruent, then the intercepted chords are congruent. So in this circle down below, the 2 central angles are angles ACB and angles ECD, the ones that have those little like kind of purple angle marker. And we know that they're congruent because they each have 1 tick mark on them. So that kind of checks off like the first box of the theorem. So if 2 central angles in a circle are congruent, we got that. Then their intercepted chords are congruent. In this case, the intercepted chords are going to be chord AB and chord ED. So then we know that the intercepted chords are congruent, and that means that they're the same exact length as each other. So chord AB would be congruent to chord ED. And then moving on to the second theorem in the middle. So it says if 2 arcs are congruent, then the intercepted central angles are congruent. So in this case, our arcs, our arc AB, remember an arc is like kind of like the crust of the pizza. So arc AB is congruent to arc ED. We know that because they each have the 1 tick mark. And then that means that their intercepted central angles are congruent. So those would be angle ACB and angle ECD inside there. So because the 2 arcs are congruent, we know that their intercepted angles or central angles are also congruent. And then the last theorem, if 2 chords in a circle are congruent, so if we have 2 chords in a circle that are congruent, then their corresponding arcs are congruent. So in this case, we have chord AB that is congruent to chord ED. And then because those are congruent, we know also that their corresponding arcs are congruent. Again, arc is like kind of the outside part of the circle. So it would mean that arc AB is congruent to arc ED. Not that they would be congruent to the chords themselves, but they're congruent to each other. So if chord AB is congruent to chord ED, then the arcs that go along with them would be congruent to each other. Okay, so example 1, angle ACB is congruent to angle DCE. What is the length of DE? So I'm going to leave this zoomed out for now just so I can reference the theorem. It's going to go along with the theorem right above it where we have 2 central angles that are congruent, and that means that their chords are congruent. So if their chords are congruent and we're trying to find the length of 1 chord, like we are with DE, we know that each of these are the same length, or they're congruent to each other, and they just have expressions, so we can take those expressions and set them equal to each other and then eventually solve for x and use that x to find the length of DE. So we're going to do 9x minus 52 equals 3x plus 11. So 9x minus 52 equals 3x plus 11. Now I have an equation that I can solve. My first priority is going to be to get my x's on the same side of the equation. So I'm going to cancel out that 3x by subtracting it from both sides. 9x minus 3x is going to leave me with 6x. And then I'll bring down the minus 52. 3x minus 3x is going to cancel out to 0. And then I'll bring down the 11. And then from there, now my priority is just getting the x by itself. So I want to cancel out that 52 that's being subtracted by adding it to both sides. And then I'll bring down the 6x. Negative 52 plus 52 is 0, so that cancels out. And then I have 11 plus 52 is 63. And then now, still trying to get x by itself, but I just have a 6 that's being multiplied by x, so I would cancel it out with division. So I would divide both sides by 6. 6 divided by 6 goes away, and it would leave me with just x. And then 63 divided by 6 would be 10.5. And then this question itself is asking for what is the length of DE. So DE is 3x plus 11. So now that we have x, we just have to take that 10.5 and put it into the x and then simplify. So it would be 3 and then times, instead of times x, would be 10.5 because that was the x we just found, and then plus 11. And then now that we're ready to simplify, we just need to make sure that we follow order of operations. So 3 times 10.5 is 31.5, and then plus 11 would be 42.5. So we end up with the length of segment DE is 42.5 for our final answer. Okay, moving on to example 2, it says arc TW is congruent to arc YZ. What is the value of X? Okay, so arc TW, let's see, is right here. And arc YZ is right here. And those are congruent to each other. And for this one, we actually need to use, let's see, this theorem over here on the right, where it says if two chords in a circle are congruent, then their corresponding arcs are congruent. So it actually kind of uses like the reverse of that theorem. So in that theorem, we have the chords that are congruent, then we know their arcs are congruent. We're just going to use like the converse of that, where if the arcs are congruent, then their chords are also congruent. So we know that the arcs are congruent. That's given to us. Because the arcs are congruent, that means that the chords are congruent as well. So chord TW and chord ZY would be congruent. And if we want to find the value of X, because those lengths or those segments are congruent, we can just set the expressions that go with them equal to each other. So I'm going to do 5x minus 26 from chord YZ. And then equals 3x minus 12. And it doesn't really matter which one you put first, whether it's like the 5x minus 26 or the 3x minus 12. Order doesn't matter there. And then now we just want to solve for x. So we're going to try to get our x's on the same side of the equation. So to do that, I'm going to subtract 3x from both sides. So 5x minus 3x is 2x. And then I'm going to bring down this minus 26. And then 3x minus 3x is 0. That cancels out. And then I would bring down the minus 12. And then now my focus is on just isolating x, so getting the x by itself. So I want to cancel out that minus 26 by adding 26 to both sides. So then I'll bring down my 2x. Negative 26 plus 26 cancels out. And then I bring down my equal sign, and negative 12 plus 26 is 14. And then now I just want to get rid of that 2 that's being multiplied by x. So to cancel out the 2 that's being multiplied, I'll divide both sides by 2. So 2 divided by 2 is just 1. That leaves me with just a regular 1x, or just x. And then 7 divided by 2 is 4. I just said that backwards. 14 divided by 2 is 7. And then this question is asking just for what is the value of x. It's not asking for the length of the actual segment. So that means we get to stop there as soon as we find the value of x. Okay, in example 3, segment MN, so this one right here, is congruent to segment KL. What is the value of x? So for that one, it's involving, you can see like we're given the 2 central angles, and then we're given 2 chords. So we have to find the theorem that involves the central angles with the chords. So that's back to this first one actually. And if we know that it's going to be like kind of like the reverse of that first theorem. So the original theorem says if 2 central angles in a circle are congruent, then the intercepted chords are congruent. In this case, we know that the chords are congruent. And so we have to use that to confirm that the central angles are congruent. Okay, so I'm going to zoom back in on this one. Again, we know like the chords are equal to each other, or congruent to each other. That's given to us, and we can use that information to confirm that the 2 central angles are congruent as well. And if we want to solve for x, we just need to take those expressions that go with each central angle and set them equal to each other. Okay, so angle MCN is going to be congruent to angle KCL, so we can take those 2 little expressions and set them equal. So I'll do 7 x minus 23 equals 5x plus 15. Same kind of setup as the other examples where we have x's on different sides of the equal sign, so I want to get them together. So I'm going to subtract 5x from both sides. So 7x minus 5x is 2x. Bring down the minus 23. And then 5x minus 5x is 0. That cancels out, and I'll bring down the 15. And then now my priority is isolating x. So I'm going to cancel out the 23 that's being subtracted by adding it to both sides. And then bring down my 2x. Negative 23 plus 23 is 0. 15 plus 23 is 38. And then that 2 is being multiplied by x. So if I want to cancel it out, I need to divide both sides by 2. And then 2 divided by 2, that cancels out. And now I'm just left with x equals 19. So check to see what the question is asking. This one is asking for what is the value of x. So that means that we can stop there as soon as we get x. We don't have to put it back into either the expressions to find like the angle or anything like that. Okay, so just to kind of summarize this section just kind of connects central angles, chords, which are like inside the circle, and arcs. So to run through the theorems one more time, the first one up here is saying that if two central angles are the same, then the chord they open up to will be the same, because it's kind of like cutting the same slice of pizza. And then the second theorem, if two arcs are the same measurement, then their central angles will be the same measurement. It's kind of like almost the reverse, but not quite at the first theorem. And then the third one, if two chords in a circle are congruent, then their corresponding arcs are congruent. So like a chord is just kind of like a measurement of the inside of a pizza slice, and an arc is like the measurement of the outside of the pizza slice. So it makes sense that if like two chords are equal, then the crust part is going to be the same. Okay, so moving down to 16.2, this is circumscribed angles. So this is a new vocab. So a circumscribed tongue twister. Okay, a circumscribed angle is an angle whose rays are tangent to the circle. So in this picture, we have like angle Q inside here. That is a circumscribed angle because the rays that help create it, PQ and PR, or the segments that help create the angle, are tangent to that circle at point P and at point R. So it's just a specific type of angle, or it has a specific relationship to a circle. Okay, moving down to the theorem, the measure of a circumscribed angle is equal to 180 degrees minus the measure of the central angle that intercepts the same arc. So I will link a quick explanation of why that is the case, but I'm not going to get into it here just for time's sake. One quick reminder is that the measure of a central angle and the arc it intercepts are the same. So like in this graphic, the central angle would be PCR, and the way that we measure arc PR, they would be the same degree measurement. So like, let's say this angle inside here was like, I don't know, 110 degrees. That would be the same measure as arc PR. They would be the same. Okay, so moving down to example 1, we're going to find these two angle measurements. So first, the measure of angle LCN, which is this one right here. And we know the measure of arc NL is 124.76 degrees. Well, the measure of the central angle that opens up to that arc is going to be the same. So arc NL is going to have the same measurement as angle LCN. And so that means that angle LCN is going to be 124.76 degrees. So we know those two, that's from a previous lesson where it says that the central angle and the arc it opens up to are the same measurement. And then for part B, we need that new theorem. So the measure of a circumscribed angle is equal to 180 minus the measure of the central angle that intercepts it. So the measure of angle LMN, that's this one right here, that's the circumscribed angle. So I'm going to just kind of like take this theorem and almost write it as like a formula to reference back to. So it's going to be, I'll write it down below here. So it'll be the circumscribed angle is equal to 180 degrees minus the central angle. So in this case, the circumscribed angle is angle LMN. So that's going to be equal to 180 degrees minus the central angle, which we just said the central angle was 124.76 degrees. So now we just need to subtract them. So we'll do 180 degrees minus 124.76 degrees, and that ends up being 55.24. 55.24 degrees is the measure of that circumscribed angle, and that's again angle LMN. Okay, example 2, this is the last example of these notes. Find the value of x. So in this case, we're not given really any of the actual angle measurements, just the expressions that we can use to eventually find them. So in this one, we have an arc and we have a circumscribed angle. So this angle inside here, angle Q, is our circumscribed angle just by definition. And then we know the measure for arc PR. And we know that that also ends up being the same exact measure as that central angle C. So the arc and the central angle, those go together. And then I'm actually going to zoom out and take this like same exact formula that I kind of wrote right here. And again, this formula is just like kind of like the math version of the theorem. So the theorem says that part highlighted in yellow, it says the circumscribed angle is equal to 180 degrees minus the measure of the central angle. So if we take the information from the picture in example 2 and we put it into that formula, I think I'm going to shrink this down because it's a little bit big. So the circumscribed angle, that's the angle like outside of the circle where the rays open up to, or the segments open up to those like the circle and are tangent to the circle. So our circumscribed angle is that 8x minus 3. So I'm going to go ahead and take that 8x minus 3 and put it in here. So it'd be 8x minus 3 equals, and then it'd be 180 minus the central angle, which the central angle is the same as the arc. So that would be 30x minus 7. And then that'll go here. And since there's multiple terms and we're subtracting, we need to put it in parentheses to make sure that we subtract the whole thing. Okay, so it's the circumscribed angle, 8x minus 3, that's the one that's outside of the circle, is equal to 180 degrees minus the central angle, which again is the same as the arc. And the arc is 30x minus 7 degrees. Okay, so now that we have it all set up, we just need to make sure that we simplify correctly and solve for x. So I'm going to leave the 8x minus 3 by itself. And then I'm going to go ahead and distribute the negative. So we'll do equals 180 degrees. And then distribute the negative in as if this is like a -1 that we're multiplying into the parentheses. So it'll be -1 times 30x, which is -30x, and then -1 times -7, which would turn it into a +7. So that's what you have to do to ensure that you are actually like subtracting the entire central angle, because if you don't, then it would just be like minus 30x minus 7. And because you're subtracting it, you have to apply that negative to each term to make sure you are subtracting the full thing, or else it'll end up being incorrect. Okay, so now I'm just going to go ahead and take off the like degrees on the 180 just because we're just dealing with x's here. My priority now is going to be to get my like x's on the same side and to combine like terms if I can. So like here I have 180 and I have a 7 that I can go ahead and combine. So it'd be 8x minus 3 equals 180 plus 7, so 187 minus 30x. And then now I want to get my x's on the same side of the equal sign. So I'm going to cancel out that 30x by adding it to both sides this time because it's negative. So 8x plus 30x is 38x. And then I'll bring down that minus 3 equals 187. And then negative 30x plus 30x cancels out. And then now I'll work on getting x completely isolated. So I'm going to add 3 to both sides to get rid of that minus 3. So then I'll have 38x, and then negative 3 plus 3 cancels out. If I add 187 plus 3, that would be 190. And then now I just need to get x completely by itself. So I'm going to divide both sides by 38 because that 38 is being multiplied by the x. So to cancel it out, I would divide both sides by 38. So 38 divided by 38 cancels out and it leaves me with just x. And then 190 divided by 38 is 5. So I end up with x equals 5. And then just refer back to like what the question is asking. It's asking to find just the value of x. So that means that we can stop there and that the value of x is equal to 5.